Thank you very much. I'm Stuart Ingleby from the University of Strathclyde in Glasgow, Scotland. It's very exciting to be presenting some of our work to you this afternoon, and I'd like to very much thank the organisers for giving me the opportunity to do so. My talk is maybe a little bit of a change of pace. I feel like there's an awful lot of engineering and not much atomic physics in it, because essentially it's all about how to take this lab-based magnetometer and squeeze all of these components down into something that's handheld, and you can start to demonstrate it to people who are interested in applying it. So we're talking about really engaging with the end users for the technology. So what I'm going to do during the talk is set that context, talk about what applications we are focused on at Strathclyde, and hopefully that motivates some of the design choices that we've made. And then I'm going to talk about the practical steps that we've taken to take each of the key subsystems of our magnetometer and turn it into something scalable, something that's closer to commercial applications, and how we've tried to preserve some of the performance there. And along the way I'll present a couple of case studies. So this is end user demonstration work that we've done and some of the results from that work. So first bit, the applications. So our work is primarily funded by the UK's Quantum Technology Hub in Sensors and Metrology. So this sets the goalpost from the start. We have to be focused on applications. The aim here is to produce demonstration systems that we can use with end users in their applications. And there was a really good comment at by Ronnie Stoltz at the QSM meeting this week, where what he said was, it's very useful to have performance metrics, but what end users really want to see is their data being taken better with your sensor. And that to me is the point of taking the sensor and demonstrating it in these kind of applications. So this is how the application space for optically pumped magnetometers kind of looks from my point of view. I've divided it up into shielded and unshielded, and my intention here is really to show that for unshielded magnetometers, if you can make them portable and make them work in the earth field, possibly even in noisy environments, then there is access to quite a wide range of applications where they can have impact. So that's been the focus of our work. It's all about portable unshielded sensors, and I've given some examples of the specific applications, but they kind of fall into three big bins there at the bottom, and I'll touch on a couple of those during the talk. So given these two criteria, that our magnetometer has to be unshielded, possibly even in a noisy unshielded environment, and it has to be portable, that kind of motivates some of the design choices. Before I get launched into those, I'll show you the first case study that I want to talk about, and this is one that we did at quite an early stage in the project. So veterinary MCG maybe sounds a bit niche, maybe a bit of a novelty measurement, but the motivation here is commercial. There's the dairy industry is a lot of money. It's billions of dollars, I think, worldwide. It's hundreds of millions of pounds in the UK. And the trend there is for larger and larger farms with more and more cows and less people. So there's already a high degree of automation in the dairy industry, and so our work here was really to perform a feasibility study to see if there was a role in there for atomic magnetometry, or optically pumped magnetometry I should say, to perform an automated non-contact measurement of the MCG signal from a cow. This is somewhere where we talk about the advantages of MCG for human healthcare. Those I think have been quite well covered, but I can't emphasize enough the non-contact nature. If you think that putting electrodes on a person for an ECG measurement is easy, it's not easy for a cow, it's expensive. This is not something that can be used for screening of infectious conditions, but actually the cardio signal in cows is quite a good indicator for conditions like mastitis that can be devastating. So we performed a feasibility study. We used a couple of Q-spin QTFM sensors because our sensors weren't ready at this point. And what we really did was the systems integration part. And these were the collaborators that we worked with. Innovate UK are the funding body for this. And I would, the data there is noisy, but as a feasibility study, it's a success. We've shown that we can detect that MCG signal, and we've validated that by comparison with the ECG. So this is the kind of thing that we were designing sensors to do. And the sensor design that we've implemented is as simple as possible. So our whole design philosophy, if you like, is to take as much out of this optics package as possible and put as much of the complexity into the embedded processor package as we can. So we're now working with a relatively small optics system that includes the laser, the cell, the detector and everything. There's a MEMS cell in the middle of that. There is a single mode VCSEL here. This is linearly polarized light that is pumping and probing these cesium atoms in this microfabricated cell. The polarimeter is a luxury item, but it's very useful for cancelling some of the noise from our VCSEL laser. And really this is chosen for the atoms, I should say, are modulated with an RF field modulation, which is again a nice sort of cheap and easy way of doing it compared to maybe optical modulation. And all of this is controlled and read out and fed back from from an embedded processing data acquisition. So the sensor package is getting on for the right size, weight and power. And what we're really trying to do is push the performance further by doing as much of that in our processing and as little of that with additional optical components. So how do we get there? First thing I'd like to talk about is the microfabricated cell. So this will be very familiar to a lot of people, but at Strathclyde we've started making these cells. We have access to a wide range of facilities, and we have the expertise within the group to use those. Our cells are based on an etched silicon wafer, that's the blue bit, and they're closed with anodic bonding of glass onto the front and back. There's a couple of different ways of getting the cesium in there, but the challenge for us, initially at least, was to make sure that we understood the maths right and didn't make any fundamental mistakes in the cell design or the gas pressure. So in the unshielded regime, we kind of assumed that we were not going to have access to some nice techniques to suppress spin exchange noise. What we wanted to do is ensure that we had a cell where spin exchange noise was correctly traded off against all the other relaxation processes. So this is the sort of model that we've used to estimate the relaxation rate in the cell. You can do similar calculations for the optical depth and the signal amplitude, and so you can work out roughly what your magnetic sensitivity should be as a function of the minimum cell dimension. So typically that's set by the thickness of the cesium wafer, thickness of the silicon wafer, I should say, and the operating temperature. So these are the kind of curves that we're calculating. For each of these, there is a buffer gas pressure optimization going on in the background, and so we can see that if all we have is 1 millimeter silicon, then the cell is kind of at its best at about 95 degrees centigrade, and we maybe have 2 or 3 kilohertz relaxation rate is what we expect, which will set the transfer function of your frequency to magnetic field and limit your sensitivity. If we can move from 1 millimeter to 2, and this is the cell that we've fabricated and used in these tests, then we bring the operating temperature down quite a bit, and now we're maybe sitting a little bit north of a kilohertz relaxation rate for that cell. And the 5mm plot that's on there is obviously a lot better, but that is what we'd like to have. It's quite difficult to obtain and etch silicon 5mm thick. So what we have in these tests is this 2mm cell. And the next question is about how to heat that cell. Again, there's a wide variety of methods here. So we could have a large cell that's operating at ambient temperature, but then when you take, apart from the difficulties of making that large cell in quantities at low cost, then when you take it out and maybe do a measurement on a typical day in Glasgow, where the weather might change from by sort of 10 degrees centigrade, the wind chill might change rapidly, then the thermal stability of that unheated large cell is potentially problematic for you. Hot air or hot water as a non-magnetic heater might be very nice from a noise point of view, but the difficulty of doing that in a small package with a low size, weight and power is really prohibiting that. So then we come down to the two approaches that we tried in practice. You have this gated ohmic heater, like Evor's magnetometer that we were talking about earlier on, which is a very efficient way of heating that cell. But the limitations on duty cycle and the kind of effects that you get from the cell temperature changing over the course of a measurement made that difficult to use in practice. So what we've done in our sensor package is move the heater current to 1 megahertz so that we can heat continuously with a well-insulated cell. It's maybe not the most efficient thing from the electronics point of view. I can say that there's an amplifier on our circuit board that gets hot, but so does the cell, and we can recover the sort of 1 kilohertz line width that we should be getting from the cell calculation. So we now have a source of cells that we can produce, and we can heat them to the temperature that's best for these measurements. So the next question is about how to miniaturize the laser, and there's been a lot of very nice sensors presented where the laser is in a big box somewhere else and there's a fiber and you have a very non-magnetic sensor package. Again, for sort of efficiency and power reasons, what I wanted to do was miniaturize the laser as well and just have an electrical connection between the control box and the sensor head. So we're using a VCSEL on the D1 line of these cesium atoms. It has electrothermal feedback to a tech that's integrated into the package. We have a part per million current driver to supply the diode bias. And the other tricky part is providing a collimation mount to that VCSEL, but with a bit of practice on the 3D printer we got there. We get single mode output 200 microwatts, and this is one of the examples of what we can do by having smarter firmware. We can economize a little bit on hardware, because what we can do is dither the temperature of the VCSEL and lock to the highest magnetic resonance amplitude. So the amplitude of the resonance is an orthogonal piece of information that comes out of your demodulation. We can lock the RF to the phase, and we have this orthogonal resonance amplitude that comes out of it. And so we can lock the VCSEL temperature to the amplitude and get just an extra order of magnitude better stability in the resonance amplitude. So you see, this is the sort of range by which that amplitude is varying as we leave our sensor to measure the field. And we don't need an independent reference cell to do that. This is something that we can do in that small package. So with these subsystems in place, we did another collaborative research project, this time in the defence and security sector. And what we've got there, this is a slightly larger package than the one that I've just showed you. It's sort of the version before. There was 2 of these with all the analog drivers that I've talked about, and some commercial data acquisition that allowed us to do a low latency locked type of measurement and a higher sampling rate open loop measurement. So we characterised the noise, and I think we're still We can certainly tell a difference between a very noisy indoor environment with our friends downstairs that Carolyn was talking about yesterday. The encouraging thing for me is that we can resolve noise and that we have a relatively flat noise spectrum in a quiet environment. The sensitivity, I think, to be really interesting in these applications, the sensitivity we need is still an order of magnitude better. I think everyone would agree with that. But it was very interesting and very encouraging feedback from the collaborators that we spoke to, particularly the end users who were Thales in this case. This is an example of the kind of discrimination that you can do with the bandwidth that's available. I realise that this plot maybe falls foul of Peter Schwindt's golden rule about normalising your noise spectra by your bandwidth. The bandwidth of this sensor is somewhere around 1 kilohertz, so really the red should continue to the top there. But the encouraging thing is that what we have here is a drone being operated nearby. You can see the motors running up, changing frequency, reaching full power, and then turning off. And this is all nicely resolved from the 50 hertz mains noise in the background. So this is an example of the sort of things that you can show to a user where you've got some functionality there that gives you signal discrimination. And this was one of the bits of good feedback that we got from the end user. So what's the next thing? I mean, this sort of double commercial data acquisition in that last system was maybe not ideal, and in the long run what we want to do is replace that with our own FPGA-based DAC unit. So we're almost to the point of marrying up our DAC unit with our sensor package. There's a lot of things to talk about in here. Needless to say, it does all the things that we need it to, provides all the feedback in loop now instead of having a bit of software that does it. The thing that I really want you to take away from this architecture is the most useful part is the user space over here, because what that allows you to do is build in user-specific features to your system. So some of our users want to take the sensor and leave it to run itself for a long time and log that data locally. They don't want the sensor to be visible at all. In the user space, you can set that up for them, compared to other users that would like to have a nice interface that they can connect to simply and interact directly with the sensor. So that's a nice architecture, and that will be the main thing that moves our system forward in the next few months. So, it's bringing me towards the end. Just to sum up, I think in unshielded sensors there is a large application space, particularly if you can produce something that is at a size, weight and power that's more like a fluxgate sensor than say a maybe more sophisticated atomic magnetometer. In order to get there, we've demonstrated a few subsystems. Our sensitivity needs a bit of a push, but the critical thing in what we're doing is that we're now starting to directly engage end users with the sensor that we're producing, and that I think moves us a lot closer to the sort of point where it becomes a commercially viable technology for us anyway. So yeah, thank you very much for your attention, and I'll leave with that. Thank you.